In our do now today, we're going back to a literal equation where we have multiple variables and we're asked to solve for x. So that means we're going to be isolating x, getting the x by itself. Here as a first step, we would want to multiply both sides by 4y to get those to cancel. We can multiply 4y and g, making it something like 4yg or 4gy equals 12x plus 3. Right? Now it looks more like a familiar equation where we can subtract 3 from both sides. 4yg and the minus 3 are unlike terms, so we cannot combine them, which means we're just going to rewrite our subtraction horizontally. So we see 4yg minus 3 equals 12x. And then now we're able to fully isolate x by dividing both sides by 12. With this, now we have 4yg minus 3 over 12 is equal to x. You might notice that 4 and 12 have a common factor. Negative 3 and 12 have a different common factor, which means we can split these into two separate fractions over 12 in order to reduce these. So that'll give us, the 4 and the 12 will cancel, giving us yg over 3 minus 1 over 4 equals x. On our second lesson of solving literal equations, we're going to add in some strategies we didn't see before, which is squaring and square rooting, as well as factoring. So we want to remember squaring and square rooting, those are inverse operations. Okay, and again, right, we're thinking about PEMDAS, whereas we're solving, we're going sort of the opposite direction, but sometimes we have to do things in a little bit of a different order to sort of uncover and reveal options. Okay. So if I look at our first example, y equals the square root of x minus 3. So I might say, oh, well, I've got to get rid of that minus 3, so I'll add it, then I can do everything else. But I can't because it's trapped underneath the radical. So I first have to get rid of the radical by squaring it. So I have to square the whole expression on the right, what's under the radical, and then square what's on the left, which is just our y. When I do that, that undoes the square root. So now I just have x minus 3 on that side. And then on the left side, I have y squared. So now that x minus 3 is free, and I can add 3 to both sides. So we've got y squared plus 3 is equal to x. Okay. Our second example, y plus 4 to the second power equals x minus 6. We're going to solve for y. The y is trapped in those parentheses with the exponent of 2. So I've got to undo that. To undo squaring, we take the square root. So I take the square root of what's on the left, and then I take the square root of what's on the right. Taking the square root of something being squared cancels out that exponent, and now we're just left with y plus 4. Right? Now that that's not being squared anymore, we don't need those parentheses either. Then on the right side, we have square root of x minus 6. Now all that's left is subtract 4. Okay, so we're going to have y equals. On the right side, it might be tempting to combine those like terms of negative 6 minus 4 and say, oh, it's negative 10. But you can't, because that negative 6 is really the square root of subtracting 6. So they're not like terms because one has a square root and one doesn't. So they can't be combined. So our answer is just y equals the square root of x minus 6 minus 4, where that minus 4 is not under the radical. And that's as much as we can go, as far as we can combine. Now our third example is a little different. So we've got x equals m plus 3my, and we're going to solve for m. So all our m's are on the right side. My first instinct might be to try to kind of subtract the 3my. So I get x minus 3my equals m, where I have an m by itself on the right side. But then I still have the m on the left side. So I might think, oh, well, I can divide by 3 and y, and it just doesn't work there. I get the intention of trying to do that first, but it doesn't work. So really what we need to notice is that each one of these terms on the right side has an m, meaning that the m is a common factor. So we can factor out the m from both of those terms. And we just do that on the right side. It's just rewriting it as an equivalent expression in a different format where we factored out the m. So that's going to be x equals m times 1 plus 3y. Now we should notice inside those parentheses, there's no m anymore. That's being multiplied to the m on the outside. So to undo that, I'm going to divide both sides by the 1 plus 3y. So it cancels on the right. And then on the left, I'm just going to have x over 1 plus 3y equals m. So m equals x over 1 plus 3y. It's the first time we're seeing factoring being used that way, so it's okay if it's a little uncomfortable. It's just something you have to adjust to, a way to get that m out of the both terms, and then we can divide. Here, let's do one more example where we wind up having to factor. Looking at this cx plus d equals bx, I know we're going to have to factor because the variable we're being asked to solve for, x, I see it twice in our equation. What's different than the last example we just looked at is those terms with x are not on the same side of the equation. So what I want to do first is get the terms with x all to one side of the equation by themselves. So bx already has x and is on its own side, so I'm going to subtract cx from both sides to get it to the right side. And now we have d equals bx minus cx. Now that I have all the terms with x by themselves, we can factor out the x, leaving the b minus c as those leftover factors in parentheses. We are isolating x, so rather than distributing or dividing by x, we're instead going to divide both sides by b minus c. So we get x equals d over b minus c.